Every hour worldwide, there are dozens of nuclear reactions, but only a few know that at the heart of every atomic bomb is a material capable of destroying a city in seconds. This isn't just a weapon, it's a miniature star, created by human hands. You will learn how ordinary uranium gives birth to an explosion with the force of thousands of suns, why the sand in New Mexico turned to glass, and what happened to an island that no longer exists. And most importantly, what secret is hidden inside a nuclear warhead? Watch until the end, because the finale will change your perception of the modern world. In ancient times, when the world was just learning to hear the voice of the atom, a few curious minds peered into the invisible, into the heart of matter. Those were the years when science was fumbling in the dark, but with great aspiration. German chemist Otto Hahn, along with Fritz Strassmann, like alchemists of a new world, discovered uranium can be split. It was like ice cracking on a river, under which a giant was sleeping. While Europe was preparing for war, a group of people, later to be called the Lords of the Atomic Flame, secretly gathered across the ocean. The Manhattan Project began in the New Mexico desert. Ordinary physicists, Oppenheimer, Fermi, Teller, became the creators of the greatest force humanity had ever seen. In the summer of 1945, under the dawn clouds, the first nuclear bomb exploded. The sand turned to glass, the sky to fire. And amidst the complete silence, one scientist whispered, "Now I am become death, the destroyer of worlds." But the story didn't end there. A few days later, Hiroshima and Nagasaki became pages of sorrow. And when the world thought it had seen everything, the USSR responded. Under the leadership of Igor Kurchatov, the first Soviet atomic bomb exploded in 1949, and a decade later, the Tsar Bomba. Its power could destroy a city the size of Paris. The irony of history is that nuclear weapons became not a sword, but a shield. Their existence forced enemies to talk. The ideas of security, control, and diplomacy became more important than combat. For the first time, humanity posed global questions. Can we agree to survive together? Thus, the doctrine of deterrence emerged. Do not attack, because you know that an attack will turn into a catastrophe. And although this balance can hardly be called ideal, it provided decades without a global war between superpowers. An entire era, cold, anxious, but without massive fronts. Nuclear research gave birth to new fields: nuclear energy, reactors on submarines, medical diagnostics. Even space projects received a boost thanks to the understanding of the atom. To create the most terrible, we learned to comprehend the most complex. Yes, nuclear weapons are a danger, but they are also a mirror of human wisdom. We created something super powerful and did not use it on a massive scale. This is a story about a force that we decided to restrain. About a science that taught us not to dominate, but to coexist. In the depths of laboratories, where the light of lamps dimly illuminates blueprints, the journey to creating a nuclear bomb begins. This is not just an assembly of metal. It is the alchemy of modernity, where every gram of substance has the power of 1,000 suns. It all starts with uranium or plutonium, isotopes capable of sustaining a chain reaction. But uranium in nature is mostly uranium-238, which is not suitable, so it is enriched. The 235 isotope is separated using centrifuges, where gaseous uranium spins at insane speeds. Plutonium is artificial. It is obtained in nuclear reactors, where uranium absorbs neutrons and turns into the plutonium needed for a nuclear bomb. The external appearance of a nuclear bomb often resembles a classic aerial bomb, a streamlined metal body designed for stable descent from a great height. In a huge hangar, where the walls ring with the echo of metal, the air smells of hot steel and lubricant. Here begins the birth of the shell that must contain the heart of the atomic explosion. From the red-hot maw of an industrial furnace comes a stream of metal, a special steel, reinforced with nickel, chromium, and manganese. Its temperature is over 1,000 degrees Fahrenheit. The summer sun pales in comparison to this fire. Masters, in protective suits with transparent shields, watch the forming. On presses with a force of hundreds of tons, a steel sheet is bent into a streamlined shape. Before their eyes, an elongated body is born, resembling a drop of water, frozen under the pressure of the heavens. Next, mechanical arms mill internal partitions. Cut holes for tail stabilizers and locks. Every millimeter is the result of careful calculation, because the balance during the fall depends on it. After this, the body undergoes a strengthening ritual. Immersion in an anti-corrosion bath, treatment with a polymer coating, and a matte paint finish. The color is dark green, similar to a military shadow on a slope of pines. And finally, testing. It is dropped from a height, struck with hammers, rotated in a wind tunnel. A quiet laboratory, semi-darkness, a light smell of ozone. Something heavy hangs in the air. Before you lies an open nuclear bomb, its metal walls removed, and its insides, like an organism, lie exposed. There is nothing superfluous here. No shine, no decorations. Only function, only explosion. At the center, a smooth, perfect sphere. It looks like a dull meteorite. This is the nuclear charge. Plutonium-239, cold and deadly, or uranium-235, heavy as a planet in the palm of your hand. Its shape is mathematical perfection, polished to the micron. Around this sphere is a whole symphony of pressure. Composite explosives, layer by layer, resemble a flower, folded inside out. Their task is not just to explode, but to make the explosion happen inside. Like palms squeezing to the limit, these explosive lenses must create an implosion, a uniform, ruthless compression that will make the substance supercritical. If even 1 second is delayed, the entire structure will become a meaningless pile of metal. And in the very heart of this implosion orchestra, the initiator. A small device waiting for the moment to release the first neutrons. Polonium and beryllium interact, creating a tiny storm capable of starting the irreversible. It is from this that the chain reaction will begin. A match to an atomic forest. Then, a layer of tamper. Heavy as a shadow, it envelops the heart of the bomb, not to protect, but to contain. Uranium-238 or tungsten are not active, but extremely important. Their task is to delay the neutrons, to make them return, like an echo in a cave. The duration of the explosion, its power, its apex, all depend on this. In the tail of the body, the brain. Automation, electronics, wires and sensors. Barometers await altitude. Radars watch the ground. Batteries slumber, ready to awaken. Here it is decided when everything must happen. Over a city, in the air, after the fall. Without this nervous system, the explosion would be an accident. But here it is, a calculation. If you look at the entire structure in cross-section, it resembles the layers of a planet, the sections of an encyclopedia of power. The outer casing, smooth and cold, the layer of explosives, mathematically arranged, the tamper, an invisible guardian, the core, like the seed of the future, and in the very center, a spark that sleeps until it is awakened. In 62 years, 2,065 nuclear explosions have occurred in the world. 5,224 is not the number of nuclear explosions, but an approximate estimate of the total US arsenal, including active, reserve, and dismantled warheads. But the number of nuclear tests that the US conducted from 1945 to 1992 is 1,154 explosions, and each of them is a separate page in the history of power, fear, and science. The first explosion, Trinity, on July 16, 1945, in the New Mexico desert. This was the beginning of an era when the energy of the atom became a weapon. It was followed by Hiroshima and Nagasaki, the only instances of the combat use of nuclear weapons. In the following decades, the US tested bombs on the atolls of Eniwetok and Bikini, in Nevada, underground, in the atmosphere, and over water. The explosions had different purposes. Testing new designs, demonstrating power, studying the effects on technology and living organisms. The power varied, from a few kilotons to 15 megatons, as in the Castle Bravo test of 1954. In 1952, the US conducted the first thermonuclear test, Ivy Mike. This was no longer just a bomb, but a miniature star created by man. The explosion destroyed an entire island. In the 1960s, testing became regular. The US tested warheads for missiles, aerial bombs, and even neutron charges, which had a minimal blast wave but maximum radiation. The last official explosion took place on September 23, 1992, after which the US declared a moratorium. But the arsenal remained. It is being modernized, adapted, and maintained. Some warheads are on submarines, some on strategic bombers, and some in NATO storage facilities. These explosions are not just technical events, they are a story of how humanity learned to control the energy of the stars and put it at the service of fear. Every year, billions of dollars are spent worldwide on developing military technologies. But only one aircraft has become a true ghost in the sky, as invisible as death itself. Its creation cost over $23 billion, united more than 40,000 people from 46 states, and even required the construction of a new industrial city. If you found out what is hidden under its black coating, you would never look at aviation the same way again. Does your country participate in the production of components for military aviation? Let us know in the comments. The design of the B-2 Spirit strategic bomber began in 1979, when the Cold War was reaching its peak. It was then that the US Department of Defense initiated the Advanced Technology Bomber program, with the goal of creating a new generation aircraft capable of penetrating the most advanced Soviet air defense systems while remaining invisible to radars and delivering nuclear or conventional weapons over intercontinental distances. Leading American aerospace corporations participated in the competition: Northrop, Boeing, Lockheed, Rockwell. After a lengthy stage of development and testing, in October 1971, the Northrop-Boeing consortium was declared the winner. It was their project that received the designation B-2 and the name Spirit. Unlike previous strategic bombers, the B-2 was built on a unique flying wing design, which provided minimal radar cross-section and significantly better flight technical characteristics. In the mid-1980s, the B-2's design had to be significantly changed. The mission profile was adapted for low-altitude flights with terrain following, which allowed for even more effective penetration of Soviet air defenses. This led to a 2-year delay in the first flight and a $1 billion increase in the program's cost. By 1989, about $23 billion had been spent on the B-2's development, and even specialists from the Massachusetts Institute of Technology were involved in the work, assessing the aircraft's effectiveness under conditions of strict secrecy. The first public showing of the B-2 Spirit took place on November 22, 1988, at Plant 42 in Palmdale, California, which is where it was assembled. The first flight of the B-2 took place on July 17, 1989. Initially, the US Air Force planned to order 132 aircraft, but after the end of the Cold War and the collapse of the USSR, as well as due to the extremely high cost, the series was reduced first to 75 and then to 21 units, including a prototype, 5 pre-production, and 15 production machines. Almost all B-2s received their own names in honor of American states, emphasizing their uniqueness and symbolic significance for the country. Thus, the B-2 Spirit became not only a technological breakthrough, but also a symbol of American military might at the turn of the 20th and 21st centuries. The production of the B-2 Spirit began not with the manufacturing of individual parts, but with the creation of a completely new industrial ecosystem capable of meeting the unique requirements for technology, materials, and assembly precision. The first and most important stage was the organization of the production base and the development of tools that did not exist before. After the design phase was completed, Northrop Grumman, as the prime contractor, invested over $1,200,000 in creating a specialized integrated composites center in Pico Rivera, California. For this, a former Ford auto plant was repurposed, turning it into one of the world's largest composite manufacturing centers. The production of the B-2 required the development of not only new materials, but also special tools, software, testing laboratories, and automated production systems. At this stage, the following were created: unique molds and tooling for forming large composite panels, automated lines for laying carbon fiber, computerized systems for cutting and shaping parts, and autoclaves for heat-treating composites at a temperature of about 350 degrees Fahrenheit and a pressure of 100 psi. The production of the B-2 began with digital modeling. Engineers created three-dimensional CAD models and then directly manufactured production tools from them, bypassing traditional mock-ups. This allowed for achieving unprecedented accuracy. Even microscopic deviations could affect the aircraft's stealth characteristics. In parallel, a complex network of contractors and suppliers was formed. Over 6,000 companies and 40,000 workers from 46 states of the US were involved in manufacturing components. Boeing was responsible for manufacturing the outer wing sections, Vought aircraft for numerous composite elements, Hughes for radar systems, and General Electric for the engines. Only after the creation of this entire infrastructure did the direct manufacturing of parts, their processing, quality control, and subsequent assembly of the aircraft at the main plant in Palmdale, California, begin. Thus, the production of the B-2 Spirit started with large-scale preparation of the production environment, engineering innovations, and the development of new technologies, which made the creation of this unique aircraft possible. After the large-scale preparation of the production base, the creation of unique tools, and the establishment of material supply chains, the direct manufacturing process of the B-2 Spirit began. Events then unfolded in several key stages, each requiring engineering precision and strict coordination among thousands of specialists and hundreds of contractors. Manufacturing of the main fuselage and wing sections. The manufacturing of the main fuselage and wing sections of the B-2 Spirit began with the production of the world's largest composite aviation parts at that time. The central part with the crew cabin was manufactured by Northrop Grumman, while Boeing made the 65-foot-long outer wing sections and the 50-foot-long aft section. The slightest deviations could affect the B-2's radar cross-section. In total, over 10,000 composite components were manufactured for one aircraft, using the latest automation and quality control technologies of that time. The precision assembly of the B-2 Spirit is a true engineering feat that unfolded in huge hangars specially created for this project. The assembly of the main sections took place on massive jigs, special platforms that occupied an area comparable to a football field. Here, hundreds of engineers, assemblers, and quality controllers worked simultaneously, each responsible for their narrow stage. Thanks to three-dimensional CAD modeling, all parts fit together perfectly. During assembly, laser measurement systems were used, which allowed for tracking accuracy down to thousandths of an inch. Even microscopic deviations could disrupt the aerodynamics or reduce the effectiveness of the stealth coating. Every joint seam was checked several times, and after connecting the sections, it was manually sealed with special materials to ensure airtightness and invisibility. The scale of the assembly was impressive. Just the central fuselage section required over 1,000 hours of labor, and the total assembly cycle for one aircraft took more than a year. All stages were accompanied by multi-level quality control, from geometry to electromagnetic compatibility. It was thanks to such attention to detail that the B-2 Spirit became a benchmark of precision and technological excellence in world aviation. After assembling the main structure, the integration of systems began. Electronics, hydraulics, fuel tanks, engines, flight control systems, radar complexes, and so on. Many subsystems had to be redesigned and adapted to the unique requirements of the stealth architecture. For example, placing the engines inside the wing to reduce infrared radiation. One of the most complex stages was the application of a multi-layer radar absorbent coating. The process took place in special hangars with a controlled microclimate. Each layer was applied by hand and then checked for defects that could increase radar cross-section. After completing the assembly and integration of all systems, the aircraft underwent multi-level tests, static and dynamic structural tests, checks of all systems operation, flight tests in various modes, and special radar cross-section tests. Any identified deficiencies were eliminated, and individual nodes could be reworked or even manufactured anew. After all tests were completed, the aircraft was officially handed over to the US Air Force. In parallel, crews were trained, undergoing specialized training on simulators and in real flights. After the production of the B-2 Spirit ended in 2000, these unique aircraft did not become museum exhibits. On the contrary, they remain at the forefront of technological progress thanks to constant improvement. The US Air Force is investing billions of dollars in modernizing each of the existing B-2s to ensure they meet current and future challenges. One of the main areas of modernization is updating the onboard control systems. Outdated analog instruments are gradually being replaced with modern digital interfaces, which increases reliability, convenience for the crew, and allows for the quick integration of new functions. The crew cabin has been equipped with multifunctional displays, and the flight control system has received new software that provides even greater stability and precision in controlling the flying wing. Did you know that over 100 million AK-47 pattern rifles have been produced worldwide since its invention? That's an absolutely staggering number, more than all the service rifles produced by almost every other country combined. This iconic weapon, recognized globally for its ruggedness and reliability, might seem incredibly simple on the outside. But producing these millions of units requires a massive, complex industrial process involving extreme forces, surprising precision, and manufacturing secrets perfected over decades. Get ready to go behind the curtain and see exactly how an AK-47 is manufactured on a colossal industrial scale. The story of the AK-47's manufacture really begins with its design philosophy. Mikhail Kalashnikov intended it to be simple, easy to use, reliable in the worst conditions, and crucially, easy and cheap to manufacture in vast numbers. This design genius meant engineers had to figure out how to make complex parts ruggedly and quickly. The key was often using methods that didn't require extreme precision machining on every single component, focusing tight tolerances only where absolutely necessary for function. This is a core secret behind its mass production success. One of the most visually impressive and important manufacturing processes for the AK-47 is IAE's stamping. Unlike many other rifles that use heavier, milled receivers, the AK-47 often uses a receiver made from sheet metal. Picture huge rolls of steel sheet being fed into massive, powerful presses. These presses stamp out the receiver's shape in stages, bending, forming, and punching the metal with tons of force. This high-speed stamping process is incredibly efficient, churning out receivers faster and cheaper than almost any other method. It's a core reason millions could be made. While the receiver is often stamped, many critical components that face extreme stress and heat, like the barrel, the bolt carrier, and the bolt itself, are made by forging. This involves heating steel billets, solid blocks of high-strength steel, to incredible temperatures until they're red-hot and malleable. Then, giant forging presses or hammers pound or squeeze these glowing pieces into complex shapes. The force involved is immense, thousands of tons, reshaping the metal's internal grain structure to make the part incredibly strong and durable. This is where raw power meets shaping, creating components tough enough to withstand the explosive forces of firing. Even though simplicity was key, certain areas of the AK-47 require remarkable machining crudelties, precision for reliable function. The bolt, which locks into the receiver, and the chamber end of the barrel, where the cartridge sits, must meet tight tolerances. These parts are finished on computer numerical control machines that use hardened cutting tools to shape the tough steel with incredible accuracy. While not every surface needs mirror-like precision, the critical interfaces that ensure safe and reliable firing are machined to exact specifications, often measured in thousandths of an inch. Bringing all these parts together involves other vital metalworking processes. Welding is used to join stamped receiver components and attach parts like the gas block to the barrel. Industrial welding robots, or skilled human welders, create strong, reliable joints. Heat treatment is also critical. Components like the bolt and bolt carrier undergo processes like hardening and tempering, heating and cooling cycles that change the steel's properties, making them incredibly resistant to wear and impact, vital for the rifle's legendary durability in harsh conditions. Once all the metal components are fabricated and treated, they often go through finishing. This includes processes like parkerizing, bluing, or applying polymer coatings. These aren't just for looks. They're crucial for protecting the metal from corrosion, especially important for a rifle designed to operate in wet, muddy, or humid environments. Furniture, the stock, handguard, and pistol grip, is often made on separate lines from wood or polymer, and then added to the metal assembly. The final stage is Korblau assembly. While many steps are automated, putting together the hundreds of components of an AK-47 often still involves significant human skill on assembly lines. Workers fit parts together, install springs, pins, and levers, turning a pile of components into a functional rifle. Each rifle is inspected visually and functionally as it comes off the line. The true test of an AK-47's manufacturing is its legendary reliability, and this is verified through rigorous quality control and testing. Rifles are subjected to dimensional checks and material tests. Crucially, they undergo proof testing, firing rounds with an intentionally heavier charge than standard to ensure the weapon can safely withstand extreme pressure. Some are even subjected to brutal environmental tests, dunked in mud, buried in sand, submerged in water, and then expected to fire immediately. This extreme testing validates the ruggedness built into the manufacturing process. Producing millions of AK-47s requires vast factory complexes, intricate logistics, and a highly skilled workforce. It's a fascinating intersection of design philosophy, focused on simplicity, and industrial processes capable of achieving rugged reliability on an unprecedented scale. While the rifle itself is often seen as a symbol of conflict, its manufacturing process is undeniably a powerful example of mass production engineering and durability-focused fabrication. So, the next time you see an image of that instantly recognizable silhouette, remember the unseen journey it took. From raw steel and wood, through giant stamping presses, powerful forging hammers, precise machining centers, intense heat treatments, and rigorous testing, it's a product of a massive, impressive industrial process. It's a fascinating look into the power and precision that builds one of the world's most widespread tools. What part of manufacturing an AK-47 surprised you the most? Let us know in the comments. Every hour worldwide, people eat over 500 tons of popcorn. That's more than the weight of 2 Boeing 747 jets. But have you ever stopped to think that inside every single kernel, there's a miniature steam boiler that explodes with enough power to increase its size by 50 times? It all begins in ancient caves in Mexico and ends up in ultra-modern factories where hot air waves, optical sorters, and cheese powder sprayers create that perfect crunch you love. Ready to see how a simple corn kernel turns into the explosive taste of your childhood? Then don't blink. It's about to get even tastier. Popcorn is one of the oldest snacks in the world. Archaeologists have found corn kernels that could still pop in caves in Mexico and Peru, and they're over 5,000 years old. And here's a cool fact. Some of those old kernels were actually still capable of turning into popcorn in a microwave today. Can you imagine that? The first people to start eating popcorn were Native American tribes, like the Maya, Aztecs, and Incas. For them, it wasn't just a treat. Popcorn had ritual significance. They used it in ceremonies, decorated idols with it, and even made jewelry and necklaces from it. Popcorn was kind of like a gift for the spirits. Popcorn made its way to North America thanks to the local tribes, and they were the ones who introduced the early settlers to this wonder. There's a legend that at the very first Thanksgiving in 1621, popcorn was also on the table. But it wasn't until the 19th century that popcorn really started becoming popular among Americans. People used to pop it right in skillets over a fire, and then, boom! In 1885, the first street vending machine for making popcorn appeared, created by Charles Cretors. And that was it. Popcorn went out into the world. First to fairs, then to movie theaters. The Great Depression really brought popcorn its fame. It was cheap, tasty, and fun. A little bit of comfort during tough times. That's why it's still associated with coziness, entertainment, and childhood today. Popcorn isn't just regular corn. It's a special variety, Zea Mesa Verta, the only one that can explode when heated. And it all starts in the field. Popcorn corn kernels are planted in the spring when the soil has warmed up enough, usually at a temperature of at least 50 degrees Fahrenheit. Fields are often chosen in drier regions because popcorn doesn't like too much moisture, which can spoil the kernel. In the United States, the main farms are located in the states of Indiana, Illinois, Nebraska, and Iowa. The plants grow slower than regular corn, but the result is worth it. It's important to wait for the cobs to fully mature. The kernels need to be hard, with low moisture content, so they pop well when heated. After harvesting, the cobs are dried, first naturally and then in special dryers, where the moisture level is brought down to an ideal 13 or 14%. Next, the cobs are shelled. The kernels are separated from the cobs using special machines. Then, the kernels go through a sorting system. Only whole kernels, uniform in size, are selected because the quality of the pop depends on this. After sorting, the kernels are packed into bags or containers and sent to factories or processing centers, where they'll be turned into the familiar popcorn we all know. Salty, sweet, caramel flavored, or even with cheese. After harvesting, drying, and sorting, the corn kernels are transported to specialized facilities. A typical popcorn plant in the United States processes up to 500,000 pounds of kernels per week. The biggest players in the market, Conagra, Pop Secret, Act 2, have their own supply networks and completely control the process from the field to the package. The kernels arrive at the factory in trucks, carrying up to 50,000 pounds of corn at a time. The truck dumps the kernels into a receiving pit where they move along a conveyor belt to the cleaning and inspection line. A sample is taken from the batch and placed in a laboratory moisture meter. The ideal moisture level is about 14%. If it's higher or lower, the batch won't proceed, or it's sent for drying. To check the physical quality of the corn, a sample of kernels is placed in an optical sorter. It scans each kernel with cameras under bright light, and it automatically rejects kernels that are chipped, have dark spots, fungus, or a different color. Also, an operator can manually check the percentage of debris, stones, hulls, and insect-damaged kernels. According to US standards, no more than 2% defective kernels per batch. It's mandatory to check how many kernels pop during a test heating. A good variety yields a minimum of 98% popping. After all checks, the kernels are cleaned, polished, and calibrated. They are often treated with special food additives or oils that improve texture, flavor, and shelf life. Popcorn comes in two main types: kernels for microwave or popcorn machines, and already popped, flavored, and packaged popcorn. The kernels are poured into heated drums, huge steel cylinders that rotate with a dull thud. Inside is dry air, heated to 450 degrees Fahrenheit. That's a temperature at which steel darkens and paper ignites in seconds. Hundreds of thousands of corn kernels continuously rotate, heating up from all sides. Inside each kernel, moisture gradually turns into steam, but it can't escape. The hard outer shell, which withstands incredible pressure, keeps it locked in like a miniature boiler. The tension builds, and then pop, pop, pop. The kernels burst with a characteristic sound that can be heard even through the drum casing. It's like fireworks, but instead of sparks, fluffy white popcorn snow that quickly fills the chamber. The moment a corn kernel explodes, its size increases by 40 or 50 times. It's literally a transformation, from a hard, shiny ball to a light, porous flower that immediately starts smelling like childhood, movie theaters, and salt. Everything happens in a flash. Each batch is ready in 2 minutes, and the drums work non-stop. The machine spits out hundreds of liters of hot popcorn, which immediately heads onto the flavoring stage. And this entire explosive performance is under complete control. Because what's at stake isn't just kernels, it's your perfect crunch. As soon as the corn clouds have popped in the drums, the next stage begins, creating that unforgettable flavor. Without it, popcorn is just crispy foam. With it, it's a caramel temptation, a cheesy sin, or a salty masterpiece. And it all happens on precise, computerized flavoring lines. A hot conveyor belt carries the popcorn to special coating drums where it gets its character. These drums are large, rotating cylinders with spray nozzles inside. Here, the popcorn tumbles around like on a carousel, and mixtures of salt, butter, caramel, or cheese powder are evenly sprayed under precise control of temperature and humidity. Popcorn arrives from the poppers or caramelizers hot. The temperature can reach 300 degrees Fahrenheit. To prevent kernels from sticking together and ensure crispness, the product is immediately sent onto conveyor belts or screens that are ventilated with cold air. The flow of cooling air is controlled by a computer that adjusts the temperature and speed according to the volume and type of popcorn. This allows a large batch of 500 or 1,000 pounds to cool down in 5 minutes without compromising its structure. When the popcorn reaches a temperature of about 77 degrees Fahrenheit, it is sent to automated packaging lines. It first passes through a sorting drum, where unpopped kernels and broken pieces are screened out. Only perfectly popped, light and airy kernels make it into the packaging machines. Depending on the product type, popcorn is packed into polypropylene or metallized bags, cardboard boxes, or large bags for bulk sale. Before sealing, an inert gas, usually nitrogen, is injected into the bags. This displaces oxygen, which slows down fat oxidation and extends shelf life up to 9 months without loss of quality. Then the packaging is hermetically sealed and marking is applied: manufacturing date, batch number, flavor, and ingredients. On average, one line can package 80 to 150 bags per minute, depending on size and weight. Cooled and packaged popcorn goes to palletizing and storage, or directly to distribution, to stores, movie theaters, or for online orders. Now, can you just picture this? Every single day on this planet, folks burn through over 9,900,000 barrels of oil. That's like what? 1 billion liters. Pretty wild to think about, right? But what is oil, really? How does this thick black goo actually get turned into the energy that powers our entire world? Today, we're gonna dive deep into the seriously fascinating world of oil production. We'll start with how it even forms over millions of years, then check out the incredible tech in modern wells that punch down tens of thousands of feet into the earth. We'll cover everything from those giant platforms way out in the middle of the ocean to the complex refining steps that take that raw material and turn it into clean fuel. Ready to find out the real story behind that black gold? Let's just jump in and see how natural gas really works. Folks are projecting that average oil production in the United States next year is going to hit right around 9,900,000 barrels per day. But honestly, do you even know what oil is or where it even came from in the first place? I mean, everybody talks about oil this, oil that, oil spills, oil production. But nobody ever really tells you what it actually is. Well, stick with us and we'll just break it down for you. The way oil forms is a seriously long-term project, taking millions of years. It kicks off with a bunch of organic stuff, like the leftovers from ancient plants and little critters piling up on the bottom of old seas and lakes. Over time, these plant and animal remains get buried under layers of sedimentary rocks, things like clay and sand. Then, under a ton of pressure and heat, which gets way more intense the deeper you go, that organic material starts transforming into something called kerogen. It's kind of a solid, waxy material. If the temperature keeps cranking up, hitting somewhere between 140 and 302 degrees Fahrenheit, that kerogen breaks down using heat. And bam! You end up with liquid hydrocarbons. So, yeah, that's us your oil. If you didn't find that interesting, seriously, let us know what you think is cool. Just write it down. Okay, so the oil that formed just like we explained, it actually travels through porous rock until it runs into something called a trap. Think of that as a geological structure that just stops it from moving any further. It starts building up there, and bingo, you've got yourself an oil field. It's kind of fascinating that scientists are still having debates about the exact details of this whole process, and whether oil might form in other ways too, not just from ancient organic bits. People started pulling oil out of the ground way back in ancient times. But the real deal oil boom didn't kick off until the 19th century. That's when the kerosene lamp came along. To actually get your hands on the oil, the absolute first step is figuring out precisely where it's hiding. This phase, geological exploration, is easily one of the toughest and most expensive parts of the entire oil extraction game. Scientists aren't just walking around with shovels, you know? They're using satellite images, magnetometers, seismic waves, and other super high-tech methods. Seismic surveying is actually pretty spectacular to witness. They set off controlled underground explosions in a specific area, or use special vibrating platforms to create waves that travel down through the rock layers. These waves bounce off different layers in the ground and come back up, and sensors pick them up. It's like building a three-dimensional picture of what's underground, essentially letting them see beneath the surface. Once the geologists pinpoint a promising spot, the actual drilling kicks off. A rig, whether it's sitting on land or floating out in the ocean, turns into this giant humming machine that runs non-stop 24/7. The drill string, those are steel pipes with a cutting bit on the end, bores into the earth, spinning it up to 200 rotations per minute. To keep the drill bit cool, carry rock pieces out, and stop the hole from collapsing, they pump in drilling mud. That's a thick mixture, usually water or oil-based. Modern wells can go seriously deep, ranging from 10,000 feet down to 16,000 feet. And sometimes, way deeper, up to 35,000 or even 40,000 feet. For instance, over in places like Texas or Saudi Arabia, they're drilling wells that stretch over 26,000 feet long. And often, a big section of the well goes sideways, horizontally. This lets them tap into a much bigger chunk of the oil reservoir without having to drill a bunch more vertical wells. One of these operations can cost you anywhere from a few $1,000,000 to easily tens of millions of dollars. And honestly, it doesn't always work out successfully. But if the well does turn out to be a producer, oil starts making its way to the surface, either pushed by its own natural pressure or pulled up with pumps. And that's when the next big stage begins, actually getting the oil out, processing it, and shipping it off. Speaking of major producers, Saudi Arabia is right up there as one of the biggest oil producers globally. Just back in February, Saudi Arabia was pumping out nearly 9 million barrels of oil every single day. This country actually has a solid chance to boost its standing in the energy market even further, especially since Saudi Aramco recently announced they found 14 brand new oil and gas fields right there in the country. So, once all the exploration and well drilling is completely finished, the absolutely crucial stage begins, actually pulling that oil out of the ground. If the field is really rich, the oil itself might just start pushing its way up to the surface simply from its own pressure. That's what's traditionally called a gusher. And while it might look pretty dramatic, with those big streams of black liquid shooting up into the air, these days, that method is seen as pretty old school and kind of dangerous. Modern wells are outfitted with sophisticated systems of valves and regulators that allow them to precisely control the pressure and the volume of oil that's flowing out. The oil gets to the surface through a network of pipes, and then it heads over to what's known as a processing facility. That's where they separate it from other stuff that came up with it, like associated gas, water, sand, and whatever else is mixed in. This step often happens right there at the extraction site, either on those big platforms out in the ocean or at bases on land. Separating all those impurities is a pretty cool process to watch. The oil mixed with all the extra stuff goes into this large, sealed tank, and gravity gets to work inside. Gas is light, so it floats up to the top. They collect it through an upper outlet. Water is heavy, so it settles down to the bottom. They drain it off through a lower valve. Oil is in the middle in terms of density, so it hangs out between those two layers. Now, if tiny droplets of water get kind of stuck in the oil, it's not quite as simple to separate them out. That's when they might add something called demulsifiers. These are chemicals that break up that mixture. Or they might heat the oil up a bit, which also helps those different layers split apart. But hey, let's get back to the extraction itself. Sometimes, to increase the pressure down in the rock formation, they use what are called secondary recovery methods. For instance, they might pump water, gas, or even steam into other wells. This helps to kind of push the oil towards the well they're actually producing from. Technologies like this can help them pull out up to 60% of the oil reserves from a field, whereas without them, that number could be cut in half. The average amount of oil a modern well in the United States produces is anywhere from 500 to 1,500 barrels per day. Just think about that for a second. One barrel is 42 gallons. Now multiply that by the thousands of wells operating all over the planet, and that really gives you a sense of the true scale of oil extraction. Oil by itself is actually a really complex blend of hundreds of different hydrocarbons, ranging from those lighter gases all the way up to heavy fuel oils. To get gasoline out of it, that's that light, easily ignitable part that internal combustion engines can use effectively. The raw material goes through several technically tricky stages at an oil refinery. It all kicks off with something called fractional distillation. Crude oil is first heated up to temperatures between 660 and 750 degrees Fahrenheit and then fed into a distillation column. This is a tall tower where the temperature gets cooler as you go up. Different components of the oil vaporize and rise to different heights, where they cool down, turn back into liquid, and are collected at various points. The gasoline part, it's one of the lighter ones, is typically collected at levels corresponding to temperatures between 104 and 392 degrees Fahrenheit. But simply distilling the crude oil isn't quite enough to get high-quality gasoline. You only get about 15 or 20% of the gasoline fraction this way, and most of what comes out still has stuff you don't want in it, and an octane number that's just too low. To boost the total amount of gasoline they get, they use a process called cracking. This is basically all about breaking down those long hydrocarbon molecules into shorter ones. The most common way is catalytic cracking, where heavier parts are heated up to almost 1,000 degrees Fahrenheit in the presence of catalysts. This lets them get extra gasoline from those heavier leftovers. Sometimes they also use hydrocracking, which involves hydrogen under high pressure. When it's all said and done, the percentage of gasoline you can get from just 1 ton of oil can reach 40 or 50%. That depends, of course, on the type of oil and how sophisticated the refinery is. The gasoline they get from these cracking steps usually has a low octane number, meaning it would cause knocking or detonate too early in an engine. To fix this, they put it through a process called reforming. This means rearranging the structure of the molecules at high temperatures, usually with platinum catalysts present. This really boosts the octane number, potentially all the way up to 98, making the fuel perfectly suitable for today's cars. In the very last step, they mix additives into the gasoline to improve how it works. This includes things for anti-corrosion, preventing engine knocking, cleaning the engine, and reducing environmental impact. This helps keep the engine healthy, cuts down on harmful stuff coming out of the tailpipe, and makes the fuel more efficient overall. Just one modern oil refinery can process up to 400,000 barrels of oil every single day. That's pretty impressive, especially when you stop and think that daily gasoline consumption in the United States is roughly 370 million gallons. Besides going to our homes, natural gas also gets sent to power plants, factories, and chemical facilities. For big industrial users, they need way higher pressure and volume. They're using pipes with diameters up to 48 inches and pressures up to 1,500 psi. Gas can even be turned into a liquid. They cool it way down and ship it in massive tankers across the oceans. Every minute in the United States, over 1,000 feet of copper pipe is manufactured. But behind this seemingly simple component lies large-scale production, explosive temperatures reaching 2,000 degrees Fahrenheit, and even espionage investigations. From molten lava in furnaces to laser marking under ultraviolet light, each pipe follows a journey straight out of a movie about industrial superheroes. And did you know that some people are audacious enough to counterfeit copper just by painting its surface? This story is about how real pipes are made and how to distinguish the genuine article from a dangerous fake. Let's dive into a world where every second equals a ton of metal. It all begins underground, in the copper mines of Arizona or Montana, where hundreds of thousands of tons of copper ore are extracted each year. It's crushed, washed, purified, and the output is shiny granules of pure copper. These granules go into smelting furnaces, where temperatures exceed 2,000 degrees Fahrenheit. Here, the copper transforms into molten lava. The molten copper is poured into long molds, so-called slabs, or ingots. They resemble thick orange beams, glowing white hot. These ingots are destined to become pipes, but there's still a long way to go. Pure copper in the form of ingots or cathode plates is loaded onto railroad flat cars, trailers, or even ships, and transported to rolling mills or pipe manufacturing plants. Cathode plates are thick metal sheets, approximately 3.3 inches by 3.3 inches, weighing up to several hundred pounds each. At the plant, the ingots or cathodes might first undergo additional remelting to achieve the required purity or desired shape, for instance, round billets for pipes. Then, they are heated and sent to the rolling mills. Rolling lines operate with machines boasting over 10,000 horsepower. The ingots are sent to rolling stands, machines weighing tens of tons. Giant rollers crush the hot metal, transforming it into long strips. The sight is incredible. The red-hot copper stretches out, sparks fly everywhere, and nearby, streams of water cool the metal, turning it into a shiny, almost mirror-like sheet. In modern workshops, all of this is controlled by computers. An operator sits in a glass cabin, similar to an airplane cockpit, monitoring dozens of screens. Here, every temperature, pressure, even the sheet thickness is under control. If anything goes wrong, the automation instantly stops the line. Now for the most interesting part. The copper sheets are cut into blanks. In plants where the copper sheets are still hot after rolling, powerful hydraulic or mechanical shears are used for cutting. They look like giant guillotines with massive steel blades. The sheet moves along a conveyor. An automatic sensor determines the exact cutting spot. The blades descend with immense force and slice off pieces of the required length and width. What do I mean when I say, with immense force? Sometimes it's tens of tons of pressure. All this happens in seconds, often while the sheet is still moving. That is, the line doesn't stop, and the guillotine cuts on the fly. For certain formats or thinner sheets, rotary knives are used. These are rotating steel discs that cut the copper as the sheet moves. It looks a bit like cutting pizza, only on an industrial scale. This method is suitable for narrow strips or when the sheet needs to be cut, not only crosswise but also lengthwise. In modern factories, laser or plasma cutters are used for complex shapes or high precision. A laser beam or plasma arc heats and vaporizes the copper at the point of contact. This results in a perfectly smooth cut, almost free of burrs. Lasers are used for non-standard parts or when special geometry is required. After the main cutting, the blanks may pass through special edge trimming machines that remove irregularities, sharp edges, or excess material. The cut blanks are fed into drawing machines. This is a huge press that draws the copper through a steel die. The output is a perfectly round, smooth pipe. All this happens in mere seconds. The machinery operates at incredible speed. At large plants, like Mueller Industries, they can produce over 1.5 million feet of pipe in a single shift. That's, no lie, like the distance from Chicago to Detroit. Each pipe undergoes automatic inspection. Laser scanners search for microcracks and defects, and special robots select samples for additional testing. After being drawn from the red-hot die, the copper pipe is still hot, flexible, and prone to deformation. To quickly give it stability, the pipes are automatically directed onto a conveyor, leading to special cooling pools. Inside is cold water, which creates clouds of steam upon contact with the incandescent metal. This sharp temperature drop locks the pipe's shape, preventing it from bending or losing its geometry. Cooling takes only a few tens of seconds, but is crucial for quality. Next, the pipes arrive at the precision cutting table. Here, they are met by automated robots equipped with cutting discs or hydraulic knives. They measure the length with laser sensors and quickly cut the pipe according to the standard. For example, 10, 20, or 40 feet, depending on the order. Cutting accuracy reaches tenths of a millimeter, and the speed is up to several hundred pipes per hour. After this, the pipes undergo quality control. Laser scanners check the external appearance, looking for cracks, burrs, or other defects. Rejected pieces are automatically sent back for remelting. Those that pass inspection continue along the conveyor to the marking machines. Here, a laser mark is applied to each pipe. It encodes the production date, batch number, sometimes even a QR code for tracking. This allows for precise identification of each pipe in case of claims or the need for quality analysis. After marking, the pipes might still be slightly damp from the cooling water. To prevent corrosion and ensure a perfect appearance, they are moved into drying chambers. These are tunnels with powerful fans and heating elements. In just a few minutes, the moisture completely evaporates and the pipes acquire their characteristic copper sheen. Next comes the packaging stage. Here, robotic manipulators come into play. They pick up the pipes using suction cups or grippers, very carefully stacking them into bundles of 10, 50, or 100 pieces, depending on the diameter and length. The robots work with surgical precision to avoid damaging the pipe surface and prevent deformation. After forming, the bundle is secured with metal or plastic straps for reliable fixation. Some plants add protective film or cardboard inserts to prevent scratches during transport. The finished bundles are automatically moved to warehouse platforms. There, each batch receives a logistics label with all the data about the manufacturer, dimensions, production date, and final recipient. Then, loading onto trucks or railroad flat cars. Everything happens as quickly as possible. A modern plant can prepare thousands of tons of pipe for shipment in a single day. Thanks to automation, this stage minimizes human involvement, ensures safety and accuracy, and guarantees that the pipes will arrive at the customer in impeccable condition. Oh right, I promised to tell you about the spy games. This is a real detective approach in manufacturing. Due to the high price and constant demand for copper, temptation arose for unscrupulous manufacturers or intermediaries. They started counterfeiting markings and passing off cheaper alloys, or even other metals as pure copper. Fraudsters became so brazen that they began forging documents and selling bootleg goods under the guise of reputable brands. Counterfeits can be dangerous. They often fail under pressure or corrode faster. A rupture in such a pipe can cause accidents, flooding, or fires. Counterfeiting scandals have occurred in many countries when it was discovered that a copper pipe actually contained only a thin layer of copper, with cheap metal inside. Manufacturers spent years building their reputations, and counterfeits under their name could lead to mass recalls and lawsuits. Therefore, pipes are now marked with invisible inks visible only under ultraviolet light. This helps combat counterfeiting